Alexey, and Joran. The stage is yours. Please.
Thank you. Let me share the screen. So Alenka, thank you very much for the introduction. Okay, so DrillFeel, that's our project, and it's a collaboration between NTNU, Departments of Geoscience Petroleum, and Department of Engineering Cybernetics from EA faculty, and Eindhoven University of Technology from the Netherlands. And all of this is happening under the umbrella of Brew21. So DrillFeel is the name of the project, and here in our studio, Geoscience Petroleum, it's myself, Alexey Pavlov, and Joran Visser. So Joran is a master's student from the Netherlands doing his master's here. So DrillFeel is about drilling, and drilling, it's you need drilling anywhere. You need to reach some targets deep under the ground. That's for oil and gas production. That's for CO2 storage, geothermal energy, hydrogen storage, etc. And this is a large-scale thing. So here, let me just show the pointer. Here you see, for example, this is a platform, and it needs to reach an oil and gas reservoir, which is located several kilometers below the surface. It's the same for CO2 storage, somewhat different for hydrogen and geothermal energy. But in any case, this is large-scale activity, large-scale process. You can also see here the kind of scale of the equipment we're dealing with. It's uncertain and it's safety critical. So if you just take modern wells and impose them over a city, so you would see a picture like this. This is just to give you an impression of the scale of this activity. So the drilling itself is happening with the drilling bit, something like what you see here, and it happens at the end of the well. So as we drill, at the end of the well, we crush the rock and we transport the cuttings up. So the driller sits at the top and monitors this process through screens and controls through joysticks. So here you have one joystick, on the left you have another joystick. So, and you can imagine that there is quite a distance between the driller and where the drilling actually is taking place. So it can be, modern wells can be up to 10, 12 kilometers long and at the depth of about 2 to 3 kilometers. So the question is, how can we improve the efficiency of this process? And this question is very closely linked to situational awareness for the driller of what is happening. So currently, as I said, everything what is available for our measurements is displayed on the screens, and the driller controls the process through the joysticks. And this is actually the bottleneck, because there is only a limited amount of information you can put on the screens, and there is a limited amount of information that you can perceive as a driller visually from these screens. So the question is how to solve this and how to go around this bottleneck and improve the situational awareness for the driller. And we came for inspiration to another industry, and that is automotive industry. So in cars, when we drive, we use the steering wheel to steer, but we also use the steering wheel to feel the conditions of the road, to feel the car. So it's not just steering, it's also feeling. If you have more or less modern car, it has this new functionalities like lane keeping functionality. And there, if you go outside of your lane, so then you will feel that the automatic system tries to keep you inside the lane, and you can feel it through the steering wheel. If you have in even a more modern car, you can have a fully autonomous driving. So then it's called pilot assist. So then you can just drive fully autonomously. But of course, you need, this is a safety critical process. You always need to be able to intervene, like what you are seeing here in this example, where when something goes wrong, the driver always takes takes over the control. Okay, so this is a safety critical process with many uncertainties, and we are controlling and feeling through the steering wheel. And there are a lot of similarities between this process and drilling. So drilling is also safety critical, uncertain, and complex. The driller monitors the process through multiple screens, so this is visual perception. Sometimes you have inputs from support personnel being onshore in remote support centers. In case of driving, that would be your wife or husband sitting nearby and commenting about where to go. And drilling is controlled through joysticks. But there is one difference. So you don't feel anything through joysticks. So these are just the devices to control something. And this difference is what we're addressing in our project DrillFeel. So DrillFeel uh, is allows you to feel the drilling process through the joysticks, and we use actuated joysticks for that. So this is a type of haptic feedback. So haptic means that it's through the sense of touch and force. So that's the description of the whole concept. So this is the drilling chair. You have two screens, you have two joysticks, and the idea is that instead of normal joysticks, we're using force feedback joysticks. So this is something coming from the gaming industry. And we combine it with the control system, automatic control system with data processing that controls the joysticks and it interacts with the other process. So it takes all the measurements, available measurements we have topside or downhole or from other systems. It processes them and it interacts through forces, through positions of the joystick with the driller. It's very simple. We built a prototype. So Jorn is the one behind building it with two joysticks, and we tested it. And now I will just show you one type of functionality that we have in the system. So there are more functionalities and not everything that I can disclose today. But the functionality is that it allows the driller to feel the downhole vibration. So as you drill, the drill string that translates the mechanical energy from the top to the down to the bottom, it's a large mechanical structure and it's subject to vibrations. So you can have downhole sensors or some digital twins that tell you that there is vibrations. And what the DrillFeel does, so it uh, gives you these vibrations through the joystick. So you can just you feel as if you are touching the drill string down there. So here you see one specific type of vibration, which is called stick slip, when the drilling bit gets stuck and then unwinds and then gets stuck and then unwinds again. So, and this is very bad for the drilling process. So it's important that the driller is able to identify this. So in case if the driller can just feel it through the joystick, then it's very easy. Then you just see, okay, this is stick slip, I need to do something. The current solutions for this is to have a remote support personnel monitoring the data and then communicating to the driller, okay, you have a stick slip. Or you maybe in the future you can develop some AI solution with a black box type of solution that can tell you that this is a stick slip. In both cases, the DrillFeel simplifies everything and makes a shortcut between the process and the driller. Now we created a video that demonstrates the application of this or the operation of this prototype. So that has been Jorn's domain of working. So in the beginning, sorry, I need to start it here. I hope you can see the video. So at first it looks like poltergeist, but this is actually just to demonstrate you that we can actually the joysticks are actuated and we can actually run the whole. We can control them and provide forces through the joysticks. The first scenario is feeling normal vibrations. So You can hardly see this, but you can actually feel these vibrations as, for example, in this close-up. So when the vibrations are small, you can feel something that the process is going on and it's okay. When you have high vibrations that probably you need to do something with, so then you have more high forces, just like here. Or the next scenario, when you have specific types of vibration, like for example, sleep vibrations, then the vibrations have very specific pattern. So, and this is something that is also recognizable for the driller. So when you have this, then you know, okay, this is stick sleep, and we need to change the operational parameters to go out of this mode. Okay, so what's the way forward for this technology? So first of all, relevance. Drillers' awareness has direct impact on drilling efficiency, and drilling efficiency that's basically translates to faster well construction for whatever it is, CO2 or oil and gas or geothermal, etc. And the faster well construction means reduced cost, but also reduced CO2 emissions, because especially when you do drilling offshore, then CO2 emissions are directly related to how long you drill. Okay. We did cooperate with the two industrial partners on this, and we received very positive feedback and interest from the industry. And right now we're working in particular with these partners to establish how shall we do piloting and further development and implementation, because it does require inputs on a different level than what we can do here at the university. So we made the prototype and we need to bring it forward and develop it further together with our industrial partners. And this is what we're working on now. And a bit of history. So the initial idea was formulated in 2019, and in 2020, when I had some money left on some other project, I decided that okay, now I buy the equipment for this project, for this testing, and then Corona came, and then finally, after 2 years of delay, we established the current team. I'll come back to that, and this is where we're now. So we made the first prototype. It was first and specialization project for the students. And then this fall or last fall, we demonstrated this prototype to an industry and got very positive feedback. And this is the master project that we are running now with the intention to have a full-scale prototype built and tested around the end of the year. But we also keep on developing towards new functionalities. And then the idea is to go towards cooperation with industrial partner. And the last Monday, we got an excellent news when Jorn and Olaf, another master student from the cybernetics department, they got the first innovation prize from the NTNU Faculty of Engineering that distinguished the best master thesis in their innovation potential. And that's the team. So apart from myself and Jorn, it's Olaf Ödegård. He now works in Siemens. He's the master student from cybernetics department. It's Lars Schimsland from automatic control from Department of Engineering Cybernetics, working with automatic control and optimization. And Erik Steur, he's the supervisor of Jorn at Eindhoven University of Technology in the Netherlands. And that's it. Do you have any questions?
Thank you, Alexey, for a very short and precise presentation today.